Okay, so I have a follow-on video from our last one where we had a simply supported beam and we wanted to work out what our bending stress distribution was. And we went through, worked out what our maximum moment was at this sort of, and what that internal moment was at point of maximum moment, which was 5 kilonewton meters. And then from there, we worked out what our stress distribution was. So this video, which is sort of a companion with that, is trying to determine what the internal moment is created by the bending stress distribution. So the reason I say this is, obviously the section has to be in equilibrium, and so that would mean that if we've got some bending stress here, some portion of the cross section is in tension and some portion is in compression. Well, there'd have to be a moment to balance that. And so what we want to know is, well, what is this moment? So this is the bending stress distribution that we have, and really you can think of it as, the bending stress. We've got this triangular stress distribution for both tension and compression. And so if we think of this sort of volume of stress as having some resultant, tension force or resultant compression force, we could draw it like this. And that tension and compression force will have, some distance that they act E away from each other. And so if we have, a force couple, so two forces at a given distance, it's going to equal a moment. And so we can work out what that moment will be. So in order to work out what this moment is, well, we just need to use statics. And so for the section to be in equilibrium, the first thing that needs to happen is that the sum of the forces have to equal 0, which means that the compression has to equal the tension. This is the key aspect to this. So what is the magnitude of this compression force, this resultant compression force? Well, like just any, resultant, we can think of it as kind of, we've got some stress, which is acting over a cross-section, so you can think of it kind of like a volume of stress, which we'll take down to a point load. And so we know that its maximum is going to be equal to 15 megapascal. And then, if that is this distance, in order to work out the volume, then we just need to know, well, what sort of the cross-sectional, if we know this bit, we know then what the sort of area is across here. So we work out what this volume is of this triangular prism, which would just be 15 times 100 times the width. So distance to the neutral axis, width, because it's going to be constant across the width, and then divided by 2 because it's a triangle, right? So be 15 MPa times 100 millimeters over 2 multiplied by 50 millimeters. And so this will be distance to the neutral axis. This is max stress, and this is the section width. And so this portion here is effectively just the area, and then multiplied by the width going across. And again, hopefully you can see, you've got sort of this area of the stress distribution. To get to a volume, we multiply by the section width. All right, so that's pretty straightforward. We can do some arithmetic here. And if we multiply all of this out, we get that the compression force, or the resultant compression force, C, is going to equal 37,500 newtons of force. And because some of the forces have to equal 0, compression and tension have to be the same. We've got no net axial force applied. So there's no external axial load adding on. So the only two forces are this resulting compression and tension force. So T is also going to equal 37,500 newtons. All right, well, now we've got our two forces. If we want to work out what this moment is, we just want to work out what this distance E is away. Now, because this is a triangular stress distribution, we know that it's the centroid, or where the resultant force is going to be, is at 2/3 away from this point. So 2/3 away from the neutral axis. And so if we know that, E is sort of split in halfway between these two, we know that E over 2 is simply going to be 2/3 times 100 millimeters. So again, 2/3 of this distance across there, just working out resultant forces and centroids of triangles. And so 2 times E over 2 is simply going to be 4 over 3 times 100. And that means that E equals 133.3 millimeters. All right, so now if we want to find a moment, all we got to do is sum our moments about some point. And so we could sum it about the neutral axis, but always like simplifying our mathematics if we can. And also I'm going to take our moment of inertia around the resultant force T. So if we sum our moments about T, that has to equal 0. And then we know that we've got, this moment M, we're saying counterclockwise is positive because we're doing statics. And so we can just sort of, in order to get a sign convention there, we sort of arbitrarily will say anticlockwise. So we'll have negative M plus the compression force C times its distance away, E. All that has to equal 0. So we get C times E equals M. So 37,500 newtons times 133.3 millimeters equals M. And then let's just go ahead and get this into kilonewtons and meters. To get there, we need to divide by 1,000. And then we would get that M equals 5 kilonewton meters, which is sort of what we would expect. That's what we got when we worked out what our maximum moment was. And this is good because what it means is that our internal stress is in balance with our external moment. And so, and that the section's in equilibrium. And that's important enough that we'll in fact just write it down, Internal bending moment equals the internal stress distribution. And there we go. So this is, and basically just from there. Now, this was kind of just a somewhat interesting aside for, as a companion piece with, our introduction to using bending stress and My over I. But it is something which is used a lot. So this concept of, having internal forces and then summing up with a moment, or working out what the moment generated from sort of some internal forces is, this is used in design quite often in both steel and concrete structures. And so while we won't spend a lot of time on it in this course, it is something that if you go on to designing for steel and concrete is done all the time. This sort of, and the reason we do that is we can size a member, we can determine sort of what maximum stress we want to say, ensure that the cross-section is staying elastic, or if we allow it to have some level of plastic deformation. So if we know a cross-section and we know a moment that we want to get to, and then we know a stress that we want to get to within that cross-section, well, we can then work out what moment that can take. And then we can compare that to, what our moment demand is from design. So, this technique here is a really useful technique in design, but like I said, we won't spend a lot of time on it in this course. But I hope you found that useful, and I guess with that, I want to say Thanks for watching.